So now, okay, so now let's see what's the relation between Green's theorem and areas. So let's look at it's a very simple idea. What is the idea? Imagine you have a curve like this, oriented this way, and we want to compute the area bounded by this curve. So this is the interior of C, so this is called D, and I want to compute, so this is C. What is the area? So what's the area bounded by C? We all know that the area is the double integral over d dA. This is very well known from calculus 3. So now, okay, this is a double integral. We know there is a relation between double integral and the Green's theorem. So the idea is, can we compute the area using a Green's theorem? The answer is yes. So let's look at the Green's theorem. What does Green's theorem say? Green's theorem says that the curve integral of the dr is equal to double integral df2 dx minus df1 dy. So basically, the relation can be seen if we compare this double integral. This is a double integral, this is another double integral. I want Green's theorem to give me the area. So basically, we're comparing these two. So if you all agree, we just need to find the function f. So we need to find f so that what? So that df2 by dx minus df1 dy equals 1. So we are just comparing the two integrands. This is the first integrand, this is the second integrand. If we find this function, we are done. For example, if we take f2 as x and f1 as x, then what's df2 by dx minus df1 by dy? It will be 1. So that works. If we take f2 as 2x and f1 as y, then what is df2 by dx minus df1 by dy? Remember, I want it to be 1. If you compute f2 with respect to x, differentiate this with respect to x, minus differentiate this with respect to y, it is 1. So that works also. So we can choose this. So this means the function f is xx. This means the function is 2xy. Sorry, the other way. So this means the function is y 2x, and so on. So let's select one of those functions. If we choose, for example, if we say, okay, let's take f2 as minus x and f1 as y. What is df2 by dx minus df1 by dy? What is that? It is minus 2. So if you agree, multiplying this minus 2 with negative half, that would give me the area. So now the idea, if we select the function to be negative half, so I'm multiplying the function with negative half, y and minus x, or you can say half minus y, x. Then let's apply Green's. Then what is the integral over c? It is double integral over d, df2 by dx, df1 by dy, which is double integral over d. What is df2 by dx? This is f2 with the half, remember? So it will be half minus, this is f1 differentiated with respect to y, that would give negative half again because of the negative dA, and this is double integral dA, which is the area of D, and that's what we want. Remember, we want the area of this region D we found that the integral of this function, if we take this function f, then the integral of this function, the line or the curve integral, is equal to the area. Although we have other options, remember, we had this option, but usually, so both components contribute to the area. If you look at this, only x contribute. Okay, in the end it gives you the area, but only x contributes. Here, both contributes, but not in a symmetric way. So the well-known formula, so the summary of this, it says, imagine you have a curve, a closed curve, C. This curve encloses some area, a certain area, the area of D. Of course, the area is A, the region is D. So the summary says the area of D, which is A, is equal to the line integral f dot dr. What is f? F is what we just found here. So f is half negative yx. Half negative yx. Now usually this is written as the integral. This is the half. So the first component is minus y dx. The second component is x dy. This is the area. So the idea again is we used Green's theorem. These computations follow from Green's theorem. So we used Green's theorem to compute the area inside a closed curve C. Now, of course, the question is it easier to find the area using a double integral or using Green's theorem? That depends. But in mathematics, this is just an idea that sometimes can help prove bigger results. So as an application, let's, for example, so use Green's theorem to compute the area inside the curve C. I'm giving you the curve C. So let's say we have this, we have this, we have this. So things now are a little bit complicated. This is a line segment, okay, it's a straight line. So let's just correct it. So these are the axes again. And this is my curve. So it runs all the way up to 1, 0. Then it goes this way up to, let's say, 2, 1. Then it goes straight to 0, 1. Then it goes back to 0, 0. So this is the curve C. We want the area inside this curve. So now what is the idea? So basically to find the area, we're asked to find Green's theorem. So I'm saying using Green's theorem, the area is going to be what we've written in the end. It's half the integral over C minus y dx plus x dy. Remember, this notation means that our function, the function that we are dealing with, is minus y and x, and we are computing the integral of f dot dr, of course, multiplied with this half. So we just compute this integral. Now, is it an easy integral or not? Let's see. Let's do the calculations. So basically now my curve consists of 4 line segments. So to do it as a line integral, we need to do it in 4 steps. The first line segment, the second line segment, and so on. So I'm doing it this way. For the first line segment, what is the parameterization? The t is changing, the x is changing, but the y is 0, and the t is between 0 and 1. So if you compute the line segment over, the integral over this line segment, the function of dot dr, if we take this half, then we multiply with the half, that's fine. So we compute the integral from 0 to 1. In this function f, you replace every x with t, every y with 0, so that gives you 0t dot r prime, that's r prime is 1, 0 dt, and that's 0. So this is a very simple integral. Then if you compute over the slanted from 1, so now we are doing it from 1, 0 to 2, 1. So again, you need to find a parameterization. Remember, the best parameterization for a line, you take the starting point, which is 1, 0, plus t times the difference between the terminal minus the initial. So 2 minus 1 is 1, 1 minus 0 is 1. That gives us 1 plus t and t. Now, if you compute the integral over this line segment, f dot dr, that would be from 0 to 1. Again, you go back to the function, which is minus yx. You replace every x and every y. So the y is t, minus y is minus t. The x is 1 plus t. You multiply this as a dot product with r prime, that's 1, 1 dt. And nicely, if you do the dot product, the minus t gets cancelled with t, and we are left with 1. After that, so we've done this integral, this line segment. Now we go to the third line segment, which is running from 2, 1 to 0, 1. Again, we need a parameterization. The x is changing, call it t, but the y is fixed, the y is 1. And the t is running from, so I'm not writing t is bigger than or equal, less than or equal, because t is running from 2 to 1 in this case. Sorry, 2 to 0. The x values are running from 2 to 0. So now the integral over this line segment, f dot dr is, you go back to the function of, this is minus yx, minus y, the y is 1 minus 1, x is t dot the derivative r prime is 1, 0 dt, and the limits are from 2 to 0. If you do this dot product, it's just minus 1 dt, which is 2. So we computed, so if you go back to the figure, we computed all these integrals. So the integral over this line segment was 0. The integral over the other line segment was 1. And now the integral over the third line segment is 2. So now it remains to compute the line integral. So now we are doing it over this line segment, which is running from 0, 1 to 0, 0. Again, we need to find a parameterization. In this parameterization, if you agree, the x is fixed at 0, but the y is changing. And again, the y, which is t, is running from 1 to 0. We can't say t is bigger than or equal to 1, less than or equal to 0. Now we compute this line integral. So the limits are from 1 to 0. We go back to the function. This is my function, minus yx. So the function is minus y. The y is t, minus y, that's minus t. X is 0 dot r prime is 0 and 1. And this integral is 0. So now going back to our figure, so now we computed this last line integral and we found it 0. Now we go back to the area. So what is the area? The area is half the integral. So now the summary, the area is half times the integral of dot dr, which is half times. Now what's the integral over this curve C? We just add the 4 integrals. So 0 plus 1 plus 2 plus 0, and that is 3 over 2. So this is how we use line integrals to compute the areas inside closed curves. Now again, the question is, so if you use Green's theorem, these are the computations using line integrals. Now what about if we use just double integrals?